Hello students, welcome back to CLARI Concepts. For more conceptual videos and engineering subjects, you can visit our website www.clariconcepts.com. So today in this lecture, before I move on and I inform you about the topic on which we are going to learn the conceptual clarity, on which we are going to gain the conceptual clarity, I would like to ask you several questions. First question is, have you ever seen that metallic pin, paper pin floats on surface of water? See, we all know that as per the physics, if something floats on water surface, it means that the density of the material is less than that of water. But here the metallic pin is made up of metallic material, and we all know that metallic material has way more density than the water. So it should actually sink. Why it is floating? You might have seen that insects walking on surface of water. Have you seen this ever? You might have seen that the water droplets on the leaf are of spherical shape, or sphere shape. Why is all this phenomena is taking place in nature? What is the reason behind this? The reason behind this is well explained by a phenomena called surface tension. Now let us understand what is this. So let us suppose, so before moving to that surface tension aspect, I have one interesting video for all of you to watch, which I have taken it from, Physics Girl YouTube channel. She has made a very interesting, has done very interesting experiments, and I want all of you to see those experiments. You can visit her YouTube channel as well. You see. So what a fascinating artwork you are seeing. This is basically because of surface tension. Another example she is trying to do. She has a cup of coffee, and what you can see over here is a small rolling over spherical bowl on surface of a coffee. You can see that it is rolling actually. When I say it is rolling, it means that it is behaving, the surface of coffee is behaving like a solid material, solid surface. She will also do the same experiment with another material, you can see. See a lot of bowls. So we have came across through these experiments on our day-to-day basis, on day-to-day life basis, but we have never given a thought why these kind of phenomena are happening in the nature, you see. If you look at this, see a very beautiful, all these balls are like rolling over the surface. Now a soap boat, she has made a paper boat, and then she will put it on the surface of water, and she will try to power it from the tail portion of the boat. You see how she is powering. Now why this boat is moving ahead? Again, this is moving ahead with the help of surface tension phenomena. Now this is one of the very interesting experiment. She has a jar in which water is filled, and the top of the jar is having the sieve. Sieve meaning they have a, you'll see what is there on the top portion when she will show from a closer look. You can see, see, the sieve is there, and it is actually open hole. It's not like a closed kind of container. Even she will try to prove that when she will she will pierce the pins. You see, the water is not coming out, and this is actually because of the surface tension phenomena. It is holding the water back. Now she is putting the pin. You see, the pin is visible inside the water bottle, but still water is not coming out. Right. So all this can only happen with the help of surface tension phenomena. Another example which we already saw in the first slide, she is trying to put the pin on surface of water. In this case it has sink because the surface tension has braked. Now gently she will put on the paper, and then she will take the paper out. Now when you see, the pin is actually floating on surface of water. Yes. Now the moment she will break the surface tension, the surface of water in tension, the pin will get sink into the water surface. So why is this happening? Let us understand this. See what is there. Let me clear this writings. What is there is, whenever you take any, let's say I take the water droplet on surface of any particular solid surface. Now when you look at the closer aspect of two different things, one is you take a point or a molecule which is within the surface, and you zoom into that, you will see that this molecule is surrounded by all the water molecules. That means this particular molecule is equally experiencing the attractive force, the intermolecular attractive force from all the sides. So this molecule will stay there. Now the molecules on the surface of this water droplet, on the surface, when you zoom into that, you will see that this layer of molecule are playing an active role in surface tension. Why? Because this layer of molecule makes the water surface in tension. Why? You will see that this molecule over here is attracted by all the other water molecules, but below the particular, the cohesive attractive forces, because all of these molecules are surrounded by this particular molecule. Now on the other side, we have different molecules. Let's say, for example, if droplet of water is open to atmosphere, you will have air molecules above this, air molecules. Now when this what will happen is air molecules will not have that kind of strong attractive force which water molecule will have. So air water molecule is having relatively weaker force compared to water molecule, and this will result into imbalance in the attractive force experienced by all these top molecules on the water surface, and because of which it will try to get shrink. So all of them will try to come inward, and because of which the water will become spherical in shape, and therefore this surface will try to reduce its area as much as possible. Which surface? The surface of water which is exposed to the another fluid. So I can say surface tension is tendency of a liquid surface to shrink into a minimum surface area possible. To shrink into a minimum surface area possible, you see, right? And then this particular shrink is quantified by a coefficient called surface tension coefficient. And how is that defined? It is defined as the surface tension coefficient of a liquid is the force, you remember this, is the force acting in the surface of the liquid at right angles to the line of unit length on surface of the liquid. Which means if I take a unit length, let's say if I cut the water droplet and I take 1 meter length of this water, if I cut this, I'll get something like this, this is the length and this is the water droplet, right, remaining portion. And now because I have cut this molecule, the adjacent molecules of this water surface will try to pull this up. Now if you cumulate the force, let's say the force is F and the length is, let's say, 1 meter. So this surface tension coefficient is what? It is saying that the amount of force that is experienced over a unit length, that is 1 meter of length on a surface at a right angle from the length, that is the surface tension coefficient. So this represents that amount of surface tension force per unit length of the water surface. So if I talk about air-water interface, for an air-water interface like this, the sigma value is 0.072 newtons per meter. It means what? If I take 1 meter of length from the surface of water-air interface, you will see that the force experienced due to surface tension is 0.072 newtons for a 1 meter length of the surface tension. So if you increase the length, let's say 2 meters, the force will get doubled. So surface tension coefficient will define on 1 meter length what is the surface tension force acting at a right angle from this particular length, right? Now let us understand this phenomena in 3 different aspects. So in engineering we have 3 different cases where surface tension is very very much observed. One is surface tension phenomena in droplets. So I have liquid droplets and we will study this surface tension phenomena in these droplets. Then we will study surface tension phenomena in hollow bubbles. Now see, the difference between droplet and bubble is one aspect. In droplet, if you cut the droplet, the entire droplet is filled with the water molecules. So inside the bubble, droplet, you will not see any other molecule. All the molecules within the surface of this droplet are water molecules, right? In bubble case, you will see that there is air inside the bubble, there is air outside the bubble. Bubble is only a departing surface. It has a particular thickness, right? As very thin bubble will be there. But within the bubble, there is air. Outside the bubble, there is air. So in bubble, there are 2 surfaces which are in tension. One is the inner surface, because the inner surface of the bubble molecules are in contact with the air molecules which are of the inner cavity, and also the outer surface. That means outer surface of the bubble molecules are also in touch with the outer air medium. So there are 2 air mediums in which the bubble is in contact with. So therefore you can say that the bubble has 2 surfaces in tension, whereas in droplet it is only the outer surface which is in tension, because the outer surface is the one which is in touch with the air molecules. Now in case of liquid jet, again the outer surface is the one which is in contact with the air molecules. So let us now look at all this things one by one. I will clear all this ink, just a minute. Okay, now let us talk about the first case. We will study surface tension phenomena in liquid droplet. First let me draw a droplet. Let us suppose this is a liquid droplet, just a minute. This is a liquid droplet, circular one, and I will cut down the droplet into 2 halves and I will study the behavior of only a first half. Let us say that this is a kind of droplet and this is the droplet, right? A liquid droplet. It is entirely filled with the water molecules. Now if you see over here, the surface molecules, this is the surface molecules which are in tension. Only this much, right? And let us suppose the diameter of this particular droplet is d, small d for example. Now outside the droplet, the pressure exerted on the droplet is, let's say, PO. and pressure of the liquid molecules within the droplet is, let's say, Pi. And also if you see that all these liquid molecules which are at the surface, they will be pulled by their adjacent another half of the molecules because of surface tension. And this will be based on the, so this force will be this surface tension force, right? I would say this to be surface tension force. Let me erase this. Let me write it as Fs, where Fs represents surface tension force. Now, if you look at the droplet basically is in equilibrium in nature. That means if I take one half will also be in equilibrium in nature. That means whatever forces are acting on this droplet in any direction will balance each other, right? So let me try to observe what happens to the forces along x and y. So firstly, I will see that let's say x is the direction positive rightward, and if you look at the forces acting on this droplet along the x direction, you will see there if I take the bubble and just draw the forces, one force acts over here is force due to external pressure, that is, let's say, Pu. One pressure force is force due to internal pressure, Pi, and another force that is acting because of surface tension, that is Fs. Now, if you consider x right side towards positive, if you use the balance summation of Fx equals to 0, you will find that force because of Pu positive, then force because of surface tension to be positive because it is also directed towards right hand side, and force because of the internal pressure Pi is negative, right? Let us say this is equal to 0 because it is in balance. Now, if you try to put the values of these forces, see what is value of force due to pressure Pu. I know that if a curved surface is exposed to a pressure Pu gas, if you want to find the force due to this pressure, you will use pressure into area. Now, area over here will not be spherical. If I want to, let's say if I have this circular shape, and if I have circular shape and if I have the fluid of pressure Pu exerting on the surface, I want to know that what is the amount of force acting on this surface in this particular direction. What I will do is I will project this area on the right wall first. So I will have a wall on which the area will be projected. So if I see, it will be a circular area, and that area multiplied by pressure will give you the force, right? So here the area will be what? Circular area, pi by 4 d square. So I will say force because of this pressure Pu will be Pu into pi by 4 d square plus force due to surface tension. Let us suppose sigma is surface tension coefficient. So sigma will give you force per unit length. So if you multiply length with this sigma, you will get the force, right? So what is the length on which surface tension is acting? It will be, what is the circumferential length? It is pi times d minus again force due to Pi, pressure Pi. So it is pressure into again pi by 4 d square equal to 0. So now what we will do is we will take both this term on the right hand side. So Pi will be positive firstly, Pi minus P0, and from both of them you can take pi by 4 d square common and out. Pi by 4 d square is equals to, this is as it is, sigma pi d. Now if you see from left and right, pi will get cancelled, one diameter will get cancelled. So what you remain with is Pi minus P0 equals to 4 times sigma by d. So this is one of the expression with which you can find out the difference in the pressures between the within the water or any liquid droplet between inner pressure and outer pressure. You can also say that this is delta P, difference in the pressure, is equals to 4 sigma by d, where sigma is what? Sigma is the surface tension coefficient between the liquid and the fluid which is around this liquid, right? And d is diameter of this droplet. Clear? Remember this, we will use this in the numericals. Now let us talk about surface tension in the hollow bubble. Now in hollow bubble, I will draw the hollow bubble. Let's say I will also draw this dotted line. The reason for me to draw this dotted line is because in hollow bubble, I hope you are aware that it is hollow by meaning this space will be filled with air. Also this space is filled with air. So there are two surfaces which is in tension. One is this, which is outer surface of the bubble, and one is inner surface of the bubble. There are two surfaces which is in tension. This is like a cavity. You can see outer surface is also in tension and also inner surface is in tension because inside also there is an air, right? Now if you cut this bubble in two halves and if you try to draw the geometry of this, it will be like this. There will be a kind of thickness and then this is like. So this particular thickness will be of soap kind of bubble material, and within this will be air, outside this will be air, right? And now if you try to look at the forces along x direction, you will see that let's say outside pressure is PO, inside pressure is PI, and now there are two surfaces which are in tension. So now surface tension forces will be over here also, and also on this surface, you can see on the outer surface. So let's say the diameter of this bubble is probably d. Thickness will be very, very small in nature, this thickness, so you can neglect that. So now if you want to find out the force balance, you can say that the force acting on this bubble because of pressure PO is positive, that is F due to pressure PO in right side. Force due to pressure PI is negative, force due to pressure PI, and this is Fs, right? Force due to surface tension plus force due to surface tension equal to 0. Now what will you do? We will try to put the values. Force due to PO will be what? I could say pressure PO into projected area pi by 4 d square minus force due to PI will be again pressure PI into projected area pi by 4 d square. But here if you see surface tension, on one circumferential length, the surface tension will be sigma into d into pi, sigma into pi into d. Sigma pi d. Why? Because sigma into circumferential length will be giving you the surface tension force on one of the surface. There are two such surfaces, you can put 2 over here, is equals to 0. Now you equate, you take both this term on the right hand side and keep this as it is. So it will be Pi minus PO pi by 4 d square equals to, you can say this 2 sigma pi d as it is, right? So you will cancel this 1d and pi, what you will remain is Pi minus P0 equals to 4 to the 8 sigma divided by d, final form. Also delta P over here is 8 sigma by d. So what you can say is delta P, that is pressure within the soap bubble, is 2 times higher than that of pressure in the liquid droplet of the same diameter and the same surface tension coefficient, right? Because it is 8 times sigma. In previous you have seen it is 4 times sigma. Yes. Now let us move ahead with the liquid droplet, jet. Surface tension phenomenon liquid jet. So let's say I have jet. Normally jets are of cylindrical shape, right? And if you look at the jet, it is also entirely filled with water or any liquid. Only the outer surface is in tension. So if I cut the jet in 2 halves, you will get something like this. So probably I'll keep it at inclination to get more clarity on this. And then you will have this surface and something like this. Okay. Now this surface, I will draw the surface in blue color which is in tension. Right, blue color surface, this will be in tension, these molecules. All of this will be in tension. Now let me assume that the length of the liquid droplet is, let's say, L, and the diameter of liquid droplet, let's say this is diameter, which is D. Now again pressure outside the droplet is PO, it is not droplet, it is the jet. Pressure inside the jet is PI, and the surface tension will be acting on the boundary, and the force is, let's say, Fs, right? So if I again use the same rule that positive x is right side and positive y is upward, and if I try to do summation of force along x to be equal to 0, I will get force because of pressure PO is positive along right side, minus force because of pressure PI is negative, because see, the pressure force is always normal to the surface, right? And plus because surface tension force is on the right hand side, Fs equals to 0. What is the force because of pressure, outside pressure? The force will be projected area into pressure. So pressure is PO. What is the projected area? Area is this one, projected area. So which is L multiplied by D. L multiplied by D minus force because of pressure PI is again L multiplied by D into PI, plus Fs is what? Fs is sigma into this length, total circumferential length. So sigma into, now you see, L plus D plus L plus D. So you can say 2 times L plus D. 2 times L plus D equal to 0. Now length will be really larger compared to diameter. So in comparison to length, you can neglect diameter if you want, for simplicity. So what will happen is, you can take both this on the right hand side, you will get Pi minus PO into LD. LD will be common and out. 2 sigma times L, and L will get cancelled. So Pi minus PO will be 2 times sigma by D. Or you can just say delta P will be equals to 2 times sigma by D. Clear? So this is the difference in the pressure. So we will use all these formulas in the numerical that we are going to see in the next slide. I hope you have understood the formulation of equations for all these 3 cases. surface tension equations. We will see the numericals in the next class. Thank you so much.